Intro music plays. Short logo animation. Before we dive in, let's do a quick reality check. When most people say styrofoam, they're actually talking about polystyrene foam. But did you know Styrofoam is actually a trademark name? It refers specifically to extruded polystyrene foam made by the Dow Chemical Company. Still, the term has stuck around as a catch-all for the lightweight, white foam used in coffee cups, packaging, and building insulation. Cut 2. Text on not all foam. Foam is styrofoam. So, how is this everyday marvel, this lightweight, air-filled material actually made? Buckle up, because today we're diving deep into the world of chemistry, heat, and engineering precision. Cut 2. Welcome to Civil Engineering Edge. This is Civil Engineering Edge, your ultimate hub for exploring the engineering wonders shaping our modern world. Section 1. The origin, from oil to resin. Everything starts with a molecule called styrene, a clear, oily liquid that's a byproduct of petroleum refining. Through a chemical process known as polymerization, these styrene molecules link together, forming polystyrene, a rigid, plastic material. Polystyrene is then cooled and shaped into tiny pellets. Think of them as the building blocks of foam. Visual suggestion. Animation showing molecules linking, forming long polymer chains. Section 2. Adding the magic, expansion agents. Now, rigid plastic isn't exactly foam, right? Here's where the transformation happens. To make polystyrene expand, manufacturers mix in a special ingredient, an expanding agent, usually pentane. This liquid evaporates easily, and when the pellets are later heated, the pentane turns to gas, puffing up each pellet like a mini balloon. Visual. Cross-section of a bead expanding, showing gas formation inside. Section 3. Pre-expansion, popcorn science. Next stop, the pre-expander machine. Inside, steam heats the polystyrene beads. As the temperature rises, the pentane inside vaporizes, causing each pellet to expand up to 40 times its original size. Think of it like making popcorn, only much smaller and far more scientific. Visual. Slow motion animation of pellet expansion inside steam chamber. Section 4. Shaping the foam, molding, and curing. After expansion, the beads are dried and stabilized. Then, they're sent to molding machines. Depending on the application, like a coffee cup, cooler box, or insulation board, the beads are reheated and molded into the desired shape. They fuse together, creating a solid but lightweight structure. Visual. Time-lapse of foam being molded into a cup and insulation block. Section 5. Final product. Cool, light, and useful. Once cooled, the product is ready, versatile, insulated, and incredibly light. From keeping your coffee warm to insulating skyscrapers, polystyrene foam is everywhere. Visual. Montage of everyday uses. Coffee cups, electronics packaging, building walls. Outrow the engineering edge. So the next time you hold a styrofoam cup, remember there's a whole world of chemistry and engineering behind that lightweight little object. If you found this breakdown fascinating, don't forget to hit like, subscribe, and click the bell icon for more deep dives into the world of engineering. On screen, subscribe. Civil Engineering Edge. This is Civil Engineering Edge, bringing engineering insights straight to your screen. Until next time, keep building your knowledge. Outrow music fades out. Logo animation ends. Section 6. Stabilization. Letting the foam breathe. After pre-expansion, the newly puffed up beads are left to rest and stabilize. Why? Because they're still warm and filled with vapor. During this stage known as conditioning, the beads cool down and equalize with surrounding air pressure. This rest period ensures the foam maintains a uniform size and structure during molding. Visual. Expanded beads resting in large storage silos, slowly cooling down. Section 7. Molding. Beads become blocks. Once stabilized, the expanded beads move to the molding stage. This is where polystyrene transforms from loose beads into solid, usable shapes. Beads are poured into a mold and exposed once again to steam. The heat causes the beads to expand slightly more and fuse together. The result? A rigid block, panel, or preformed item like a takeout box or insulation board. Zoom in of mold filling, beads expanding and bonding together under steam. Section 8. Final curing, strength through patience. Even after molding, the process isn't over. The shaped foam must be cured a controlled resting period that allows internal stresses to release. This curing phase ensures the final product is dimensionally stable and won't warp or crack. It's a quiet but crucial step that guarantees durability. Visual, molded blocks stacked on racks in a curing room, ambient conditions shown. Section 9. Polystyrene in construction. The unsung hero. In civil engineering, expanded polystyrene or EPS plays a critical role. It's lightweight, moisture-resistant, and offers excellent thermal insulation. From road embankments to foundation insulation, EPS helps reduce loads on weak soil, minimize heat loss, and cut down on construction costs. Time lapse of EPS sheets being installed in a building wall or bridge foundation. Section 10. Environmental concerns, a double-edged sword. Despite its benefits, polystyrene comes with environmental concerns. It's non-biodegradable and often ends up in landfills or oceans. However, the industry is evolving. New technologies are exploring biodegradable alternatives, better recycling methods, and circular manufacturing systems that can help reduce its environmental impact. Split screen. Screen showing foam waste versus recycling plant innovations. Section 11. Sustainability, reinventing the foam. Some manufacturers are now turning toward alternative blowing agents materials that help expand polystyrene but with less environmental impact. And while recycling polystyrene foam remains a challenge due to its lightweight and bulky nature, specialized facilities can compact and repurpose it into products like picture frames, crown moldings, and even new foam materials. Visual. Foam being compacted and transformed into decorative and industrial items. Section 12. Surprising facts about Styrofoam. Did you know Styrofoam is made of 95% air? That's why it's so incredibly lightweight and buoyant, yet still an excellent thermal insulator. It's the reason we find it in everything from coffee cups to cold chain packaging and building insulation systems. Visual, split screen of coffee cup, cooler box, and construction insulation layers. Section 13. A glimpse into history. Here's a bit of history. During World War II, polystyrene was first used at scale as a substitute for rubber. Its foam form was developed later and went on to revolutionize industries like packaging and construction. Visual. Archival photos of World War II supply chains, early packaging factories. Section 14. The future of foam. As we move toward a more sustainable future, research is underway to develop biodegradable versions of polystyrene foam using plant-based resins, seaweed, or even mycelium from fungi. These innovations are still emerging, but they carry the potential to dramatically reduce the environmental impact of foam materials. Visual. Scientists working in a lab, growing mycelium foam samples. Section 14A. Cost benefits of Styrofoam. Big value in a small package. When it comes to building materials, cost effectiveness is just as important as performance. And this is where Styrofoam truly excels. Because Styrofoam is made up of 95% air, it requires very little raw material to produce, making it inexpensive and efficient to manufacture. That translates to lower costs in packaging, insulation, and construction applications. Visual. Cost comparison chart. Styrofoam versus other insulation materials. Section 1 for B. Use benefits. Lightweight, durable, and versatile. From an engineering standpoint, Styrofoam offers a range of practical benefits. Lightweight, reduces transportation costs and structural load on buildings. Excellent thermal insulation, helps control indoor temperatures and energy use. Moisture resistant, ideal for damp environments or below-grade construction. Shock absorbent, protects fragile goods during transport. Moldable, easily shaped into blocks, panels, or custom designs for various uses. Whether you're insulating a building, stabilizing road embankments, or simply shipping electronics, Styrofoam delivers reliable performance at a low cost. Visual, rapid montage wall insulation, EPS under roads, shipping box, thermal container. Section 1 for C, cost versus value. Why engineers still use it? When you balance initial cost, long-term energy savings, and ease of installation, Styrofoam remains a go-to choice for civil engineers and contractors worldwide. Its ability to combine economy with efficiency makes it one of the most widely adopted materials in the industry. Visual, stacked EPS panels being loaded onto a truck, labeled light, strong, affordable. Section 15. Final thoughts. Engineering with purpose. So, there you have it, the remarkable journey of Styrofoam, from tiny polystyrene beads to the lightweight, versatile material that supports modern life. It's a process built on chemistry, engineering, and a touch of innovation. Visual, quick recap montage, chemical beads, expansion, molding, construction use. Out row. Join the engineering conversation. Yes, Styrofoam poses environmental challenges, but with human ingenuity and evolving technology, even the simplest materials can become part of a smarter, greener future. Next time you sip coffee from a foam cup or unbox a new gadget cushioned in Styrofoam, remember the science, the history, and the potential that went into making it. And who knows, maybe soon, that cup will be made from biodegradable foam grown from nature itself. Visual, foam cup dissolving into a leaf icon or green future concept. Call to action from the team at Civil Engineering Edge. Thanks for joining us on this fascinating journey through materials science with Civil Engineering Edge. If you enjoyed this video, please like, subscribe, and share it with fellow engineering minds. Have an idea for a future topic? Drop it in the comments. We might feature your suggestion in our next episode. On screen, LIKE. Subscribe, comment, Civil Engineering Edge. This is Civil Engineering Edge, where small details lead to big ideas. Until next time, stay curious and keep engineering your world. End screen with video suggestions.